Math 3 Lesson Summary Video, Rays and Radians. This lesson is a solidify and practice understanding task, which takes concepts developed previously and helps formalize those ideas while also working on and applying them to new situations. The purpose of this lesson is to examine and practice ideas and procedures associated with radians. You will also create and use a conversion factor to convert degree measurements to radians. The formula Madison has been using to calculate radian measure for an angle that measures in degrees on a circle of radius r is in degrees over 360 degrees times 2 pi r all over r is equal to x radians. Is there a simpler formula for converting degree measurement to radian measurement? And what formula might you use to convert radian measurement back to degrees? So this goes back to yesterday's lesson where we talked about radians were measured by taking the arc length over the radius of the circle. And so we find the arc length, if you remember, by finding the circumference of the circle. So this is the whole circumference of the circle, and then the proportion of the circle that it is. So what angle out of 360 is it taking up? So it's proportional thinking. But this is a fraction inside of a fraction. And in general, we don't like to keep fractions inside of fractions. So instead of maybe just thinking about it as the arc length over the radius, is there a way that we could simplify it? So let's just think of some of our algebra skills and tools that we may have. Dividing by r would be the same thing as multiplying by 1 over r. We also know that if we multiply, this is the same thing as 2 pi r over 1. So if we can get everything written as fractions, maybe we can see if we have anything that we can put together. For example, I notice pretty quickly that my r's will divide one another. R divided by r is just 1. So that's useful. I also notice that 2 and 360 can simplify. 2 is a common factor there, and so we can factor out the 2, and the 2's will divide and become 1. And so we can actually take whatever the angle measure, n was our degrees, if you recall, and if we have our n degrees and we multiply it times pi over 180, that's going to equal x amount of radians. So we were able to simplify, use some of those rational function skills and expressions that we had earlier, and get to this formula. This is also a very important proportion. If we think about it from a conversion standpoint, pi is the measurement of half of the circle in radians, and 180 is also the measure of half of a circle in degrees. So if I'm multiplying degrees by radians over degrees, the degrees will divide out and I'm left with radians. So this goes back to also thinking like in science class as a conversion. So now we know that radians is going to be equal to the number of degrees times pi over 180. Now, if we want to go back in the other direction and we want to know what is the degrees going to be equal to, well, I need to find the inverse. The inverse of pi over 180 is to multiply by the reciprocal, 180 over pi. So the number of radians times 180 over pi would work to convert it back. Madison finds this idea of writing radian measurement in terms of pi appealing. Since a circle measures 2 pi radians, she reasons that half of a circle, 180 degrees, would measure pi radians, and that a quarter of a turn, a right angle, would measure pi over 2 radians. Suddenly, Madison realizes that while she has been deep in thought thinking about this new idea, she has been fiddling with her protractor. Now her attention focuses on this tool for measuring angles. Like Madison, you've probably used a protractor to measure angles. A protractor is usually marked to measure angles in degrees. Madison decides she would like to create a protractor to measure angles in radians. So let's take a moment and think about a protractor and how would we divide it into radians. Madison already called out a couple of them for us. 0 radians and 0 degrees are still just 0. So everything on the protractor is in degrees, but we want to figure out how many radians we're dealing with. We're also thinking, let's leave it as pi. One thing we do want to start working towards is working with exact answers. And remember, pi is exact. If you take the decimal, 3.14, that's rounded. And even if you keep more decimal places, it's still rounded and an approximation. It's an irrational number, so it keeps going and going and going and going. So leaving pi in the mix actually makes it an exact number. And what Madison noticed, and we did too in our conversion earlier, was that 180 degrees is 1 pi radians. So if from here to here was pi radians, she rationalized or thought proportionally 90 degrees is half of that, so it should be half of pi. Now you can write it as half times pi. Some people prefer to write it as pi over 2. Those are the same thing, so either way that you want to write those, 90 degrees is going to be half of pi. If I keep using this same fractional thinking, half of 90 degrees is 45 degrees. 45 degrees is right here. Well, half of a half is a fourth of a pi. And again, we could write that as pi over 4. And if we went that same direction over here, 40 more is actually 135 degrees. So that would be in this direction. And if this was 1/4, this is 2/4, this is 4/4, then this must be 3/4 pi. Now you could write that as 3 pi over 4 if you wanted the pi to be in the fraction. Those again are the exact same thing. That's just a matter of how do you like to write your fractions. So those would be fractionally. We could also try to think of, they've got it counting by tens here. We want to think fractionally. When we count by tens, how many pieces of the protractor do we get? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 pieces of the protractor. So that would mean that each 10 degrees is 1/18 of the whole protractor, which we determined was pi. So 1/18 of pi would then make this 2/18 of pi, but we don't write fractions 2/18. That reduces. I don't want to leave it as 2/18. I'm going to have to reduce that down to 1/9. So 20, instead of being 2/18, is going to be 1/9 pi. So that will be pi over 9. Now 3/18. Well, that reduces too. That'll be 1/6. So this is 1/6 pi, or pi over 6. Now 4/18, well, it reduces too. Not all the way down to 1 though. It looks like 2 will go into both of these, so that's going to be 2/9. So now I have 2/9 pi, or 2 pi over 9, so forth and so on. So you can see how we're building these fractions, and now we have an exact radian measure and not just a decimal approximation.